Alrighty, thank you guys for coming out tonight. Today, we're going to talk about building Ekko. And Ekko is a real-time message processing framework. And don't worry, we're going to jump into exactly what that means. Before we dig in though, just a quick intro to our team. We're an incredibly spread out team, but this ended up being a pretty good opportunity for us. We were able to learn how to effectively collaborate remotely. And you'll be hearing from all of us throughout different parts of this presentation. A quick overview over what we'll be covering. We'll start off by talking about real-time web applications. And after that, we'll spend some time explaining why real-time web applications often need dedicated real-time infrastructure. Next, we'll go into why real-time web applications often also need real-time middleware, and we'll explain what that is. Next, we'll do a quick demo of Ekko so you could see what it actually looks like for a developer to interact with it. And after that, we'll spend some time digging into some of the more interesting engineering challenges we tackled. Finally, we'll wrap up with some resources for anyone who wants to learn more about Ekko. So first off, let's talk about real-time web applications. Real-time web applications are everywhere. They're all the live dashboards we see. They're all of the apps that show you the driver location or the package location on a map. And they're all the chat apps that we use. These are just a couple examples. When it comes to actually defining what a real-time web application is, everything centers on this idea of the user's perception. And this quote sums it up pretty nicely. It says, "A real-time interaction has a human angle, because one of the collaborators in any real-time data exchange is always a human. Hence, the human perception of a real-time event is very important." And this feels like a bit of a loose definition, but because web applications are primarily concerned with the user experience, it's actually the only definition that's really relevant. And it does lead us to some useful insights. Now, the first insight is that we have to shift our idea of how data is transferred. So if we go back to a traditional HTTP request response cycle, we have this idea of pulling data. And with pulling data, we have data that accumulates somewhere, usually in a database, and it just sits there. It doesn't go anywhere. It doesn't really go anywhere until a client explicitly makes a request for the data. And then the server responds with the data. And that's why it's called pulling data, because the client has to pull the data to them by making these explicit requests. And this is distinct from a data push pattern. And with the data push pattern, the client often does start off with a similar request, but the difference is that the client is requesting new data to be sent as soon as it is generated. And then so now we have new data that's generated and it's immediately sent to the client. It doesn't accumulate anywhere. And when we think about real-time web applications, pretty much everything follows this data push pattern. And that's in line with the idea of things being perceived as instantaneous. So going back to kind of a simple chat example, it'd be weird if you had to click a button to see if there are new messages for you. You expect them just to show up as soon as they're ready. And another interesting insight with real-time web applications is that we actually move away from the server-client model. And so the server-client model, it's very focused on the actual devices being used. But in real-time web applications, it's much more useful to focus on the roles that these devices are being used for, not the actual devices themselves. And this leads us to the pub sub pattern. And so here you'll notice that we're no longer talking about servers and clients, we're talking about publishers and subscribers. And so on the left, we have a single publisher and they're sending messages to the subscriber on the right. And that actually leads us to another interesting insight. We're no longer calling data just data, we're calling it messages when we talk about real-time web applications. And messages really are just bits of data. So it could be an actual text message, but it could also be location data or any number of things. And it's called messages because once again, we're moving away from the implementation details and focusing instead on the actual roles being played. And so expanding on this, we also have this idea of one-to-many pub sub models. And this is another fairly common pattern. And so here we still have a single publisher on the left, but now we have 3 subscribers on the right. And as the publisher generates new messages, it sends them to the subscribers. And expanding on this a little bit further, you can imagine that we can also have a many-to-many pub sub pattern. And this is a possible pattern. And there are specific protocols such as WebRTC, which are peer-to-peer protocols specifically for this type of setup. But you can see things can get kind of complicated pretty quickly just because of how many connections there are. And so for many-to-many pub sub, it's actually much more common to have a central hub. And with this pattern, each of the publishers and each of the subscribers has a single real-time connection to the central hub. And when a publisher sends a message, it goes to the hub, and then it gets emitted to all relevant subscribers. And just for one final idea that comes up often in pub sub messaging, we have this idea of bidirectional communication. And up until now, all of the devices we talked about were either a publisher or a subscriber. But within real-time web applications, it's actually very common for devices to be both publishers and subscribers. And it kind of makes sense. Once again, going back to the chat example, whenever you send a message, you're a publisher, and whenever you receive a message, you're a subscriber. And here we're showing various devices who are both publishers and subscribers. And when one of them sends a message, it goes to the central hub and gets emitted to all relevant subscribers. So now let's imagine you actually want to implement a real-time feature in one of your applications. Now, we'll start off with a fairly simple example. We'll use the example of a customer service chat box. And we'll start with a simple use case and kind of build up to the point where a lot of people do end up when you realize that managing real-time connections can be very difficult and often needs dedicated infrastructure. And so when you actually start off, a lot of times you might do some Googling or searching around for real-time. And when you do that, you'll often run into these different protocols. And this isn't an all-encompassing list, but these are definitely some of the more common ones that come up. So there's quite a few HTTP derivatives, such as server-sent events, HTTP long polling, HTTP streaming. And then there's WebRTC, which is that peer-to-peer protocol we already talked about. And then there's web transport and WebSockets. So now referring back to what we talked about previously, we know that for a real-time feature, you're going to need a data push pattern. And all of these protocols do support that. But since this is a customer service chat feature, you know it's going to need to be bidirectional, so you can both send and receive messages to customers. And that rules out pretty much all of the HTTP derivative. And there definitely are some hacks and workarounds to get this to work for bidirectional communication, but it's not the typical use case. They're all primarily set up for one directional communication. And next, you realize you already have a central application server, whatever is running the actual application you're adding the customer service chat to. So it kind of makes sense to stick with that pattern instead of trying to implement a whole peer-to-peer network to work on top of. And so using a central hub rules out WebRTC, which is a peer-to-peer protocol. Last but not least, it's probably a good idea to use something that's been proven in production. And that rules out web transport, which is a super interesting technology, but it still is an emerging technology that hasn't been fully fleshed out yet. And so that leaves you with WebSockets, and that probably makes sense. WebSockets is definitely the most common way to implement this type of feature into a web application. So let's say that you're actually going to jump in and start building a proof of concept. It's actually surprisingly simple to get up and running. You can just open up your own application code and add a WebSocket library, such as Socket.io, and that's pretty much it. It's fairly simple to get up and running. Now, there are quite a few challenges that'll arise, though, if you either want to start adding more real-time features in, or if you want to use this in production. Now, the first thing you might run into is the problem of adding additional real-time features. And this can be additional real-time features in the same application, such as adding location data or live dashboards or translation, or it can also be multiple real-time features that are the same, just across different applications. And in either case, you'll find yourself spending less and less time on your actual application code and more time just figuring out the actual real-time infrastructure needed to support this. And that's a negative pattern to fall into. Now, another issue you might run into is the issue of scaling. If any one of your applications becomes very popular and it grows to the point where it can't scale on just a single server and it needs to split out into a horizontally scaled architecture, this makes things significantly more difficult. Because there's a few reasons. One of them is that just the technology of WebSockets is more challenging to work with across different server instances. And we'll dig into some of the details of that later. But there's also the issue of the pub sub model. and trying to manage and synchronize all the publisher data and subscriber data and message data across different server instances. One final thing you might also notice is you might realize that your application needs scale at a different rate than your real-time needs. And so all of these things kind of point to the same thing. They point to the idea that managing real-time connections can be very challenging, and that if you plan on actually using a lot of these in production, it's often a good idea to have dedicated real-time infrastructure. And that's exactly what these companies do. These are some of the leading companies that provide real-time infrastructure as a service. And so for people who don't want to do it all on their own and they don't want to build their own infrastructure, you can just use one of these companies to handle all of the real-time infrastructure. And these companies all pretty much advocate the exact same thing. They all advocate the idea of decoupling the real-time infrastructure from your application. Now, if you actually continue down this path and start adding more and more real-time features into your applications, you're going to run into another idea, and that's the idea of real-time middleware. And for an example, if we take our customer service chat example once again, real-time middleware could be something like translation. So if you get to the point where you have a bunch of customers in different countries and you want to add support for these different languages, real-time middleware could be something that actually intercepts the messages, translates them into whatever language is relevant, and then sends it back out to the customer. And so that's the idea of real-time middleware, something acting in the middle of the message sending process. And some other examples are things like when you open up an Uber app, it doesn't show you every driver in the world. It just shows you the ones that are nearby you. There's some filtering going on. Additionally, for in-game chat, there's often profanity filters. And so once again, the messages are going to and from individual users, but somewhere in the middle, they're being filtered out if there's anything offensive. And then for things like chatbots, this is a screenshot of Amazon Lex, there's a lot of analysis happening on the actual messages so that the actual bot knows what to respond with. And we dug into this a little deeper and we found that there's actually quite a few different categories of real-time middleware, and they're also used all over the place. And so some of the common ones are message transformation, where the actual data in the message is being changed in some way. And then there's message enrichment, where based on the data in the message, other things are added into it. And then there's things like message filtering and chatbots, which we already talked about. And then messages are often also used to feed into data analysis or to trigger alerts and notification. And all of these are kind of the same idea. Somewhere in the middle, there's some business logic being applied. And this pattern was also recognized by PubNub and Ably. So PubNub has a great quote where they say, "You see everyone publishing down to their server, doing a small bit of processing, and then publishing the message right back out. It doesn't make sense." And Ably has a similar quote where they say, "A common requirement in real-time messaging applications is to be able to insert some business logic into a message processing pipeline." And so both of them recognize this anti-pattern in their customers, where the customers were using their service, so they had set up dedicated real-time infrastructure, but then they needed to do some sort of business logic on all the messages. So all of a sudden, all the messages from this real-time infrastructure hub were being sent down to their own application servers to do this little extra processing and then sent back out. So even though they were physically decoupling their application servers from the real-time infrastructure, they pretty much just recoupled them, and they had to make their own infrastructure as scalable as the real-time needs. And you just kind of get right back into that negative feedback loop where you have to support all of the real-time scalability needs. And so both PubNub and Ably came up with solutions for this. So PubNub came up with PubNub functions. And these are proprietary serverless functions that you can write and deploy within your PubNub dashboard. And Ably took a little bit of a different approach. They let you create serverless functions on one of many different function or serverless function providers, and then they integrate those into your Ably pipeline. And so in both cases, the end result's pretty much the same though. It's removing the business logic from your application code and putting it somewhere else. Now, we did think it was interesting that these are two of the major companies. They both recognize the exact same problem, but they solved it in very different ways, with PubNub taking an internal solution and Ably using an external one. And so this is kind of the landscape of options right now. If you want to build real-time features and add them to your applications, you can either use a third-party service, you can use an open source solution, or you can do it yourself. And each definitely has different trade-offs, and the right choice does depend very much on your specific use case. So for example, if your goal is just to have something that's easy to get up and running, you probably should go with a third-party service. Those are pretty easy to set up. Now, there are definitely some open source solutions which are pretty simple, but these definitely vary on a case-by-case basis. Now, if your goal instead, or your main priority, is to have complete control over your data and over the infrastructure, then you're going to need to go with an open source solution or a do-it-yourself solution. Now, if you want to use real-time middleware, things get a little interesting. As we showed, not all the major providers actually offer real-time middleware out of the box. And if you do use one that has that, you still will have to give up some of your control. And currently, we did a bunch of searching, and currently there are no open source solutions that have real-time middleware out of the box either. And you can obviously build pretty much anything yourself, but this is a particularly ambitious undertaking. And because there was no clear-cut obvious choice for this specific set of criteria, this is the area that we decided to dig into, which led us to eventually build Ekko. And with that, I'll pass it off to Drew.
Thanks, Will. So we saw a gap in the market, and as a result, we built Ekko. Ekko is an open source framework that you can use to deploy your own real-time infrastructure with real-time middleware. So there are four main parts to Ekko. The first is the Ekko server, and this manages the real-time messages for your applications. The second is Ekko functions, which provide that real-time middleware for in-transit message processing. And then we have the Ekko CLI, which makes it easy to manage Ekko functions and spin up and tear down the Ekko infrastructure. And the Ekko client enables you to build real-time applications on top of the Ekko server. And because Ekko is open source and self-deployed, you have complete control over the infrastructure. You can customize it to your needs, and you don't have to rely on a third party to manage your real-time data. So now that we know what Ekko is, let's try it out. First, we'll spin up our own Ekko infrastructure with our CLI tool. So the Ekko CLI tool provides us with several commands that we can use. We can add a help command or a help flag to the end of a command, and it'll show us the documentation for that command. Here we'll run Ekko init, and we'll input our AWS credentials. And this will spin up a new Ekko infrastructure for us using the AWS Cloud Development Kit. So this process normally takes 10 to 15 minutes, but we've sped it up here. It will also create a new Ekko directory in our current working directory. And it's worth noting that you can tear down your Ekko infrastructure just as easily with the Ekko teardown command. So now that we've spun up our infrastructure, let's take a look at it. So here's our Ekko infrastructure. We have our Ekko server on the top right there. And this is a node application that's deployed in a container on AWS Elastic Container Service. On the left side, there's an application load balancer, and this distributes WebSocket connections to our Ekko server. On the bottom, there's an S3 bucket and an Elasticache instance. We'll learn a little more about the role that those play later. But for now, what's important to know is that this Ekko server is what manages the real-time messages for our applications. So now let's set up a real-time application that uses the Ekko server to manage its real-time messages. Recall that when we ran Ekko init, it created an Ekko directory in our current working directory. In there, we have Ekko functions and Ekko apps. We'll look at Ekko functions later. So within Ekko apps, we have a few demo applications, and these are designed to help a developer become familiar with building real-time applications using Ekko. We'll be using the chat demo application here, and it consists of a basic HTML file. This HTML file runs a couple of scripts. The first is our Ekko client, which is stored on a CDN, and the other is this script.js. And in this script, we're creating a new Ekko client instance, and this will allow us to connect our chat demo application to our Ekko server that we just deployed. So the Ekko client instance takes a handful of parameters: an app name, a host, a JSON web token, and a UUID. We've already set our app name to chat demo, and we'll generate the host and JSON web token values with our CLI tool. The UUID is optional, so we won't worry about it here. So back in our CLI tool, let's generate the host and JSON Web Token values. We'll do this by running the echo JWT command and pass in the name of our application as the argument. So it outputs a few values, the first being that Ekko server endpoint. And this is the URL of the Ekko server that we just deployed. And again, it will allow the Ekko client to connect to the Ekko server and send real-time messages to it. The next value is this user JSON Web Token. And this is the value used by the Ekko server to verify that our chat demo app is indeed a valid Ekko client. And that last value that the CLI output is an admin token. And this is for an application server. It enables an app server to connect to a special admin channel and get status events. But our simple chat demo here doesn't need an application server, so we're not going to use this value. So now that our chat demo app can use the Ekko client to communicate with the Ekko server, let's go ahead and test it out. To do this, we'll open our HTML file in 2 different browsers to simulate 2 different Ekko clients. Both of these clients are subscribed to 4 different channels that we can think of as chat rooms: boring, angry, backwards, and robot. When one client publishes a message, it's sent out to our Ekko server that then emits that message back out to all subscribed clients, which in this case is both of them. So now let's take another look at our infrastructure and see what it looks like when we have these 2 clients connected to our Ekko server, sending real-time messages to it. You can see that we now have these 2 clients connected to our Ekko server. When one client publishes a message on the boring channel, it goes out to the Ekko server, which then emits that message back out to the subscribed clients. So we've seen how an application can use the Ekko server to manage its real-time messages. Let's go ahead and deploy some real-time middleware to process these messages in transit. So first, back in our chat demo app, we'll switch to the angry channel. And here, when we publish a message, we expect it to be transformed, capitalized with exclamation points added. But we can see that's not the case. In order to process our messages in transit, we need to deploy Ekko functions. Recall that this Ekko functions directory was created when we ran Ekko init. In it, we have a handful of demo functions that are designed to go along with our demo applications and help a developer become familiar with creating this real-time middleware. We'll check out the demo angry function here. And you can see that it has a specific file structure and format so that it can be deployed to AWS Lambda. You can see here that our demo angry function simply takes the message payload, capitalizes the text, and adds a few exclamation points. So now that we've seen how these functions work, let's go back to our CLI tool and deploy them. So with our CLI tool, we can change to the Ekko functions directory, and we can check the status of our functions. And we see here that none of them are deployed. We can easily deploy them by running the Ekko deploy command. And what this does is deploys those functions to AWS Lambda, where they can run alongside of our server. We'll run the status command again here. And we can see that those functions have been deployed. So there's one more thing we have to do. We need to run Updateassociations.json. And this is a file that the server uses in order to know which functions are associated with which channels. We'll go into a little more detail on associations.json later. So back in our chat demo, let's see if these deployed Ekko functions work. And they do. We see that our real-time messages are being processed in transit. Note that we didn't have to refresh the browser, and we didn't have to update any client-side code or any server-side code. Instead, we use Ekko functions on our local machine and deploy them to AWS Lambda to do the processing. So there are many benefits to implementing the real-time middleware in this way, and we'll get into that later. But for now, it's apparent that Ekko functions make this easy to create deploy, update, and destroy these lambdas. So now let's go see how these deployed Ekko functions work within our infrastructure. We can see on the right the Ekko functions that have been deployed to AWS Lambda. When a client sends a message on the angry channel, the server gets it and sends the message to the angry Lambda for processing, and then sends it back out to subscribed clients. The same happens on the backwards channel and the robot channel. The server knows which lambdas are associated with which channels using that associations.json file that we mentioned earlier. So now that we've seen what Ekko is and how it works, I'll turn it over to Dorey, who's going to talk about the engineering challenges that we faced while building Ekko.
Thanks, Drew. The engineering challenges we faced while building Ekko fell into three categories. The first was how to implement Ekko functions, our real-time middleware, specifically what technology we used. The second challenge was how to manage the data for linking specific Ekko functions with real-time messages. And the last was how to make sure that Ekko could scale up as load and demand increased, which Alex will explain. So let's start with the first engineering challenge, implementing Ekko functions. We needed to figure out where to handle message processing. Where do we put our real-time middleware? We're definitely not going to put it on the Ekko client because that introduces security concerns and performance problems. But we could put it on the Ekko server. However, the Ekko server would have to be redeployed every time the middleware was updated. We'd also be coupling various unrelated pieces of business logic that would need to scale up and down based on independent needs. Furthermore, we'd like to keep our separation of concerns and let the Ekko server just manage real-time connections. We could put Ekko functions on a server dedicated to message processing. It's still within our real-time service, but separate from the Ekko server. However, we'd introduce all of the same problems from putting it on the Ekko server. We'd be redeploying the server for every update and coupling unrelated pieces of logic. Another possibility would be to use serverless functions. Serverless functions allow us to break up business logic into individual pieces that can scale independently. Imagine we have a chat app that is using the Ekko server and filtering out profanity from all of its messages. We also have a geolocation-based app that needs to hydrate real-time messages with directions obtained from the Google Maps API. These two apps are both routing messages through the Ekko server, but their needs are unrelated. They have bursty traffic at different times. If we use serverless functions as our real-time middleware, we can scale the profanity filtering up without affecting the directions processing, and vice versa. Serverless functions also provide flexibility. They can be reused across multiple apps. When functions are updated or added, the rest of the real-time service is not affected. So what exactly are serverless functions? Serverless functions are pieces of code that are managed by a cloud provider, which is responsible for dynamically allocating resources to execute that code. Serverless functions are modular and reusable. They are independently scalable. They spin up on demand. They are ephemeral, and they are easy to package and deploy. However, they can't do heavy lifting. There are maximums for length of compute and size of payload. They add complexity to your infrastructure. They live on servers with other people's code. They have a cold start and can take longer to execute if spinning up for the first time. And they can be harder to test and debug. But let's go back to our use case, which is many publishers and many subscribers needing to process messages in transit, on demand, without interdependency or a need to keep track of state. Our goal was to provide a flexible framework to accommodate changing business needs. For these reasons, we thought serverless functions were a good fit for our real-time middleware. And as Will mentioned before, this also happens to be the way that Ably and PubNub both handled message processing in their services. Now let's move on to the second engineering challenge, how to manage Ekko functions. Once we determined where our real-time middleware would live, we needed to figure out how to manage it, specifically linking middleware with real-time messages. Since clients publish and subscribe to channels, it made sense to link specific channels with specific Ekko functions. So if you're making that chat app that uses a profanity filter, you can create a channel and have all messages published to that channel be processed through the profanity filter. All subscribers to that channel will receive the processed message. At this point, we wondered about the possibility of needing to use more than one Ekko function to process a message. For example, what if you now need to translate that same message in your chat app to another language? You can chain the Ekko functions so that the processed message from the profanity filter will pass through the language translation function before returning to the subscriber. The next piece to managing middleware was deciding how to store channel middleware associations. We decided on using a JSON file. Here's a sample of our file associations.json. It is organized by applications. Each application has an array of channels, and each of those channels contains an array of Ekko functions to be used for that channel. Ekko will process the message using all of the specified Ekko functions in order before returning the processed message to the subscribers. The JSON file lives on an S3 bucket, which is an AWS cloud storage service. The developer would be responsible for manually updating it locally and then uploading it with the Ekko CLI tool. We decided to just cache the associations data on the server since it didn't change very often, but we needed to figure out how to update the server nodes when a change was made to the JSON file. We looked at two ways for pushing the data to the Ekko server. The first was to use the AWS service CloudWatch to send a message through SNS, another AWS service, notifying the Ekko server that a new set of data was available to load. The second was to update the Ekko server directly at the same time that we upload the new JSON file to the S3. This would involve sending a put request to the Ekko server with the JSON file as the payload. We could just add this behind the scenes in our CLI tool when the developer uses the Ekko update command. And this was the option we chose, since it didn't add any complexity to our infrastructure. Now I'm going to show you a little demo of how to chain Ekko functions. First, we're going to create a new Ekko function. We'll call it Demo Emojify. This is going to create a new folder in the Ekko functions directory, and we'll open up the index.js file to write our message processing logic. For this function, we'll add an angry emoji before and after the message text. And then we'll return the processed message. Using the CLI tool, we deploy the new Ekko function to AWS. And we can see that that was successful. Now we need to edit our associations.json file. We're going to add demo emojify to our angry channel right after the Ekko function called demo angry. The final step is to update Ekko with our new associations.json file using the update command. As I mentioned before, the associations.json file will be uploaded to the S3 as well as sent in a put request directly to the Ekko server. Let's take a look and see Ekko function chaining in action. In our demo chat app, let's see what happens when we publish a message to the angry channel. As you can see, that was successful. It capitalized the message using the first Ekko function and added angry emojis using the second before it returned the message to the subscribers. And with that, I'll hand it over to Alex to talk about our final engineering challenge.
Thank you, Dorey. So the last of our engineering challenges that we want to mention relates to how we set up Ekko to scale horizontally. We wanted Ekko to be able to scale up and down as needed. And of course, some of this was achieved by choosing the appropriate infrastructure and policies on AWS. The main part of Ekko that needed to be able to scale were the Ekko servers. We needed to support a flexible number of users connecting to the real-time service, as well as an increased volume of messages being published. In order to be able to scale flexibly, a pretty attractive option for horizontal scaling was to package up our server application as a Docker container, and then use AWS's Fargate service to scale those server tasks up and down according to how taxed the particular task instance became. Now, Fargate scales according to rules that take into account how much CPU and memory each container is using. It's not always completely transparent to use, but it did handle our core problem that we were trying to solve of wanting to horizontally scale our Ekko server functionality. But there were some other additional problems we had to sort out. Our first challenge when scaling up to multiple instances was getting our clients to establish WebSocket connections. Our application load balancer is going to take incoming connections and pass them on to the next server node in a rotating list of available server nodes. Establishing a WebSocket connection is a two-part handshake using HTTP requests. With a default configuration of our load balancer, though, the first part of that handshake gets routed to one server node, and the second gets routed to another. We weren't able to establish our WebSocket connections when we first tried out our infrastructure on AWS for this reason. Given that we're using Fargate, though, the solution to this problem was to add some configuration to our CDK deployment code. We needed to enable sticky sessions as a policy for our managed server instances, and then each Ekko client could be routed to the same server instance it was initially assigned, and we could successfully establish WebSocket connections. Once we had established these WebSocket connections, we encountered a new challenge. Messages being published to separate servers weren't being broadcast to all of our subscribers. If we have two instances of our Ekko server, the load balancer is going to connect one user to server instance A, as you can see here on the top, and the other to server instance B below. In this scenario, they are both subscribed to the same channel so that they can chat with each other. Alice has a WebSocket connection to server A, and when she publishes her message, server A receives it and publishes that message to the channel so that all subscribers will receive it. However, only the WebSockets connected with server A will get that message, so Bob won't receive it since he's connected to server B. In order to solve this problem, we used the Socket.io Redis adapter library. This library uses a Redis instance hosted on AWS's Elasticache service to broadcast events to all of the Socket.io server nodes. Alice's message, published to server node A, is automatically emitted out to all of the subscribers, even though some of them are connected to other servers. With this infrastructure set up and with sticky sessions enabled, we did some load testing using artillery.io to validate some of our main use cases. Our first test scenario was that we wanted to make sure we were able to sustain reasonably high volumes of messages published through the Ekko server. To this end, we tested and learned that Ekko is able to sustain 50,000 messages sent per minute. Each of those messages is also in turn transformed by Lambda functions. So that's our serverless middleware. And for our test, this amounted to a total of 500,000 messages and Lambda function invocations sent over the course of 10 minutes. During the test, AWS's Elastic Container Service spun up 2 additional Ekko server containers to deal with this extra load. For our second test scenario, we wanted to make sure that we were able to support many subscribers receiving messages. Ekko is able to sustain 600,000 messages received per minute published to a single channel. We were really happy with these numbers, and actually these loads didn't max out our server capacities or cause failures, so we probably could have kept increasing the load even further, but it didn't seem like our use cases demanded that. A final engineering challenge we encountered was figuring out how to synchronize state between all of our Ekko server instances. We needed to ensure that all of these server instances had the latest version of the associations.json data, which pairs channels with the Ekko functions that will execute on all associated messages passing through. When updates are made to the associations.json file, we let the Ekko server know by sending a put request with the new associations data as the payload. However, again, we have a problem. The request will be routed to just one of our Ekko server instances. We need to be able to notify all of the Ekko server instances with the updated data. As you can see from the animation, our put request does update one of these server container instances, but this update isn't shared with the others. And our solution to this was to use the standard Redis package. The server that receives the message publishes the file to the Redis Elasticache cluster, and all the other server instances in turn are subscribed to the Redis cluster and receive a copy of the new associations data. This is what allowed us to keep our server instances in sync and share the associations data among all of them. And that's Ekko, an open source framework allowing developers to easily add real-time infrastructure and in-transit message processing to web applications. And by this point, I hope we have shown you how flexible Ekko is to work with. The possibilities available to you are many, as you can see from some of the examples above. The combination of a real-time server with serverless functions as a kind of middleware for in-transit processing of messages offers a rich palette of options. We look forward to hearing what you build with Ekko. You can test drive our code and demo applications by visiting our GitHub repository, and our case study will be available on our webpage soon as well. And with that, we welcome any questions you might have. Okay, our first question came in. What was the biggest challenge building Ekko for each of you?
I can go ahead and answer that. I found that the biggest challenge came when we started working with the AWS infrastructure, and debugging problems that arose was really challenging. So often what would happen is our server instances would just start dying and we'd have to figure out what the problem was. And it was a team effort, because sometimes, I remember one time it was something in the CDK code, and another time it had to do with the Ekko client, and another time it was the Ekko server. So, so that was a challenging part of the development process, I found.
I think for me, the most challenging, but also one of the most fun challenges we tackled was figuring out how to update that associations data in all of the server instances. And if you think about it, it's kind of a weird challenge because we're storing that in memory. So we're not like hitting a database every time. It's like actually just stored in a variable. And so figuring out how to do that on demand was pretty tricky. And we tried a ton of different things. And at one point we had like Ekko client installed on Ekko server, and it was kind of crazy. So I think our final solution of using that whole put endpoint to Redis subscription thing was pretty elegant and seemed to work really well. So that was a really fun one to tackle.
Yeah, and for me, it wasn't the biggest challenge, but I just thought it was an interesting challenge. When we first started building Ekko, we had to build the Ekko server and the Ekko client, and it's like we mentioned, it's pretty easy to build a real-time application with a library like Socket.io, but we had to figure out how to build a platform that would enable other developers to build real-time applications using our platform. And so that was just a way of thinking about building software that was completely new to me. So it was an interesting challenge.
I think for me, the biggest challenge, since I was working a lot on the infrastructure part, was actually just dealing with some of the AWS documentation for CDK, which in parts was like really opaque and difficult to find exactly what you wanted. And you ended up having to read just like literally everything to find something buried deep in a forum post that was available nowhere else. So yeah, a lot of kind of line by line reading like reams of CDK documentation, I think was the big challenge that I found. Our next question comes from, well, I didn't give the name, but what was your favorite or most rewarding part of building Ekko?
So for me, I think it was, we split our project eventually up into 4 parts where we worked synchronously for a while, and then we split up, and I worked on the CLI tool. And that was a really interesting, rewarding process because at first I just had no idea how to do something like that. And it had to do a lot. It had to use CDK or the CDK code to deploy our infrastructure, work with the Amazon Web Services SDK, send requests to the server, and manage Ekko functions. So there was so much behind it, and it seemed like this insurmountable thing to build. And then, just step by step, learning by doing, it wound up not actually being that crazy, and we found a good library to do it. And it was just a matter of working with AWS SDK and using JavaScript code to make that all happen.
I think
So
building. Oh, sorry. Go for it, Alex.
From my perspective, I think I really enjoyed the kind of ideation part before we started building Ekko, kind of generating ideas for the project. We got to go down all sorts of rabbit holes that had come up during the earlier bits of Capstone. Yeah, I really enjoyed that, reading up on just coming up with different ideas. And of course, I think like working with my teammates, that was a really kind of edifying part of the project. I feel like we spent a lot of time together that I really enjoyed.
I remember I sort of was getting to a point after we had split up where I was sort of ready to transition into some other bits of the project. And I did a lot of the initial work on that simple little chat demo that we used throughout this presentation. And I remember when I downloaded the CLI code from NPM and like install that on my machine and use it to like deploy Lambdas and actually like build this app. And it was pretty mind blowing. Like it felt like a real thing all of a sudden. And it was cool because I realized like in that moment, my brain totally flipped over where now it went from like, what are the bugs we have to solve? And all of a sudden it switched into like, what can I build with this tool? And that was definitely this like super, super gratifying moment that I don't know if I've encountered with any other projects I'd built before this. So it's definitely that fun turning point.
Yeah, I echo all of that. The teamwork part was really great. And I also enjoyed working with the AWS infrastructure and getting to experience what it was like to build something that we had only learned about conceptually. I thought that was really gratifying.
So next question, what did the MVP of Ekko look like, and or how did you begin going about building it?
We used to joke about we called it our BVP, our baby viable product, but we started with a simple WebSocket server and a client. I don't know if anyone else wants to add to that.
Yeah, it was pretty, like it was just like our demo said, like the very first like proof of concept was pretty quick to set up because it was just a little Express app with the Socket.io library. So that was something we were able to get up and running pretty quickly. And then just having like just in our actual application code, we just added a few like fake middleware things to act on the messages. So the proof of concept happened pretty quickly. And then we slowly began the trudge of like actually fleshing out a real kind of production version of it all.
So this next question asks whether it was smooth sailing working with AWS. I guess I'll take that. Probably relating to my previous answer, like it wasn't always smooth sailing. There's a lot of kind of magic that goes on with deploying stuff, particularly when you're using AWS's cloud development kit. And I think people, my other teammates will remember there was, I think, maybe a week or so where I just spent kind of banging my head against the wall, trying to get this particular configuration to be applied to our infrastructure. We could do it manually, but we couldn't do it with our deployment code. So it definitely wasn't smooth sailing. It's really nice when you know what you need to do and you know the specific little bit of snippet of code or the property that turns something on and off. But until that point, it often got frustrating.
Just to add really quickly to that, some of the parts were really easy working with the SDK, but the really painful parts seem to involve the permissions in using different services that needed to work together.
Another question, was seeing the load testing results as gratifying as I imagine?
So the short answer to that question is yes, it was. It was really cool. The load testing was definitely one of my favorite parts of the project. And what was really neat about it was that we had all spent weeks and weeks building this tool. But then when we started load testing it, we were essentially using the tool. So it was really impressive to see, Alex mentioned that one test where we set up 50,000 connections and started firing them all at the Ekko server, which then was hitting those lambdas, that middleware. And we wound up over the course of 100 seconds hitting 50 or 500,000 lambdas and 500,000 messages. And so it was just really cool to see how it actually worked and how impressive it was once we were all finished.
Another question, why did you choose the domain of real-time and more specifically real-time middleware? Any reason in particular or just because it seemed interesting?
So we first started looking at a webhooks project, and that kind of follows that data push model that Will was talking about, where a server's automatically pushing data to another server. And that sort of led us to this real-time space. We found this company, PubNub, that offered these real-time services. So we thought real-time would be a cool place to go. And then we realized that there was already an existing capstone project, a really cool project called River, that had already built a real-time service. And this was a drop-in service that developers could use to add real-time to their existing application. And so we wanted to kind of take that a step further. So River was to publish messages to many subscribers, and we wanted our service to handle that many pub sub model where you have many publishers and many subscribers. And when we dug a little deeper, we found several problems within that space that were really interesting, but we came across this real-time middleware, and the use cases behind it were really cool. And so we just decided to go in that direction with our project.
This next question relates to what features would you like to add to Ekko going forward? I think I can answer that. So we had, obviously we kind of had some trade-offs and things that we focused on during the project. But things that we wanted to add include message persistence. So allowing the messages to be stored somewhere so that if someone has a dodgy internet connection, that then Ekko can send them whatever messages they missed while they were offline. We really wanted to add encryption, kind of end-to-end encryption for the messages so that the Ekko server wouldn't need to be dealing with anyone's actual data, so that it could be encrypted in transit. And we wanted to kind of handle in-order delivery of messages, which at the moment we prioritize getting the messages to the users or the clients really fast. And with these Lambda functions, you can imagine that at certain times, if certain Lambda functions take a while to compute, perhaps, or take a little bit longer than another, you might get messages being delivered out of order. This is actually a trade-off which all of the major players in the space, PubNub, Ably, they all kind of hand off to the developer and they say, this isn't really our problem, you have to deal with this yourself. Yeah, it seems like a really juicy problem that would be really nice to add. One other question, has anyone else used this open source software? If so, how many? Who are they? Tell you that it's basically just been us, since I think everyone here is basically the first people who've been using or hearing about Ekko. And we kind of finished the project relatively recently, but it's ready for people to use. And one final question.
The unveiling of Ekko. So if any of you guys watching want to use it, feel free to and let us know how it goes.
So one final question, how different would a task like researching, planning, building Ekko be if you hadn't attended Capstone?
That's a hard one to answer. I feel like there was so much that I learned in Capstone that prepared me for understanding the problem space and how to approach it. I think it would be, how different. Yeah, it would be very different because there was just a lot of knowledge that we had before even approaching it.
I think also so much of it is like there was no magic like recipe or formula that was bestowed upon us in Capstone or anything, but there was a lot of information that just helped us avoid pitfalls. And then also there was a lot of great resources and people that kind of challenged our ideas and made sure that we were thinking about things critically and finding engineering challenges that would be kind of compelling for actual like working engineers and not just interesting, fun ideas we had. And so I think it's like there isn't any single piece out there, but just a lot of these things helped us avoid just spinning our wheels or going into weird rabbit holes that were just kind of fruitless endeavors and things. So it's like just everything was 10% more directed and 10% smoother and 10% more kind of validated. And I feel like that all adds up to a pretty big difference at the end of the day.
And with that, I think we're out of questions. So thank you very much all for showing up. We know that Capstone presentations can often feel a little bit out of reach when you are working your way through core, but we hope we've at least given you a taste for some of the things that you can build using Ekko, some of those demo footage. We'd love to hear, of course, if anyone ends up building anything using Ekko. And with that, thank you all once again.